So this is a talk about stable matchings or stable allocation in college admissions markets. It's joined with Péter, Biro, Avinatan, Hassidim, Assaf, Romm, and Sándor, Sovago. I'm Shorrer. I'm at Penn State. So stability is an important solution concept in two-sided matching markets. It's thought to be crucial for the success of centralized marketplaces, and we think it's predictive in decentralized markets. Now, the set of stable matchings is generally a set. It's not a singleton. And this multiplicity has motivated a large literature about the structure of the set, algorithms to identify kind of special elements of the set, and so on. But this literature has slowed down as more and more studies show that typically the size of this set is actually quite small. When I say that the set of stable matching is small, I mean a few things. First, I mean that the same agents are matched across all stable matchings and the same quotas are filled. That's a result known as the rural hospital theorem. But I also mean that all but a handful of agents receive the same matching in all stable matchings. Okay? And that, even more generally, payoff differences between matchings are found typically to be small. Now, there is a big literature on that. A lot of it is theoretical. Actually, many of the important papers appeared here in EC. But I want to point out that they are motivated also by empirical findings. For example, the findings of Roth and Pearson, who showed that in the American medical match, changing the orientation from doctor proposing or to hospital proposing or vice versa would only change the assignment of 20 out of 20,000 doctors. So that's the background. What are the implications of these findings? The implications are that, first, stability yields a sharp prediction, if we want to try to predict what will happen in a market. Maybe more relevant to this community, it means that if I'm a market designer and I'm interested or I'm committed to implement something stable, there is very little left to do. A related result is that manipulating deferred acceptance is very, very difficult, no matter which side of the algorithm you are. And since, in general, it's typically optimal to just be honest, there are no incentives to spy, to collect information about what others are going to do in the market, because that will not have a consequence on how agents will behave. All right. So what do we do in this paper? In this paper, we expand the framework to think about not just matching markets, where agents are matched to each other, but matching with contracts, where agents are matched under contractual terms. In particular, we think about the specific environment of college admissions, where agents can be matched to a college and pay their own tuition, or they can be funded by the state. So these are the type of contracts we'll have in mind most of the time. We show that deferred acceptance still produces a stable allocation. And we show that actually, depending on the orientation you run, you're going to get the side optimal merit-based stable allocation. We also show that in large markets, all merit-based stable matchings look alike. However, there are other stable matchings that don't allocate financial aid based on merit. And these could be quite different. In particular, they can differ in the number of assigned students. The rural hospital theorem no longer holds in such settings. A natural question that this raises is whether or not we can find the largest one. And we show that even approximating the largest cardinality stable matching is NP hard. But we come up with an algorithm which we think is practical. It's a heuristic, if you wish. And we apply it to data from Hungary, where we show that a different stable allocation than the one currently in use, which is deferred acceptance-based, would increase the number of applicants assigned to college by about 2% and would change the allocation of about 8% of the students. All right, so because this paper will follow closely the empirical setting, I want to spend just 1 minute telling you a little bit about Hungary. The Hungarian college admissions market has been centralized starting in the 80s. There are about 100,000 applicants each year. 80% more or less are assigned every year. These applicants submit rank order lists that rank alternatives. So an alternative would be a program, say economics in Penn State, and financial terms. Am I funded by the government, or do I pay my own tuition? And of course, some students may care a lot about this funding, and they may not rank positions that require them to pay, and some students may not be very sensitive to that. There is a heterogeneity in the population. There are about 2,000 programs, and what I want you to take from this slide is just that most of the capacity available in the market is concentrated in programs that offer state-funded and self-funded positions. So almost any program somebody applies to is offered in two forms. Our model of Hungarian college admission is the most natural generalization of Gale and Shapley's model. Instead of one capacity, we have two capacities. So there is a capacity of state-funded seats and a capacity of self-funded seats. The college has a strict ranking over students, and the college choice function is generalized responsive. So basically, out of the menu, the college chooses the best students that it can, subject to both of these capacities. Now, to make sure that I'm not sneaking in anything, we allow for arbitrary tie breaking that guarantees that there are no ties or indifferences. Stability is defined as usual. It's not pairwise stability. We're allowing arbitrary large coalitions to block. Yeah. So for the first part of the paper, it's very useful to construct an auxiliary market where I actually take a college and its two capacities and split it to a related matching market where each capacity behaves as its own college. You'll note that this transformation kills any incentives of each copy to collaborate with the other copy. So there is no reason for Penn State economics funded to help Penn State economics unfunded in any intuitive way. Yeah? The first lemma of the paper says that a matching, an allocation in the original market is stable and merit-based if and only if it corresponds to a stable matching in the related market. What do I mean by when I say merit-based? I mean that there are no two students in Penn State such that I is ranked higher than J, and yet J is funded and I is jealous of the funding terms of J. As a corollary, we already get a lot of things. So first, we get existence of stable allocations in the college problem. In fact, we get existence of a merit-based stable allocation. We get a rural hospital theorem that says that all merit-based stable allocations assign the same agents. We get a consensus property saying that the student optimal merit-based stable allocation is just the outcome of student proposing deferred acceptance. And we get that SPDA, student proposing deferred acceptance, is strategy proof, and SRDA, which is what we call college proposing DA, is only manipulable by students that get different assignments between these two. So let's take that to the data and compare SRDA, the mechanism that existed in the year we studied, 2007, to a change in your orientation to student proposing deferred acceptance. We find that the same number of students are matched. That's a result of the rural hospital theorem. Nobody loses, because we know that student proposing is optimal among merit-based stable allocations. And 8 students gain. So very familiar results. Basically, these are the only 8 students that could have manipulated successfully the original mechanism, and there is not much to do. But now I want to show you an example. This is a minimal example. There is one college. There are 2 students. The college has 2 seats, but only one of them is funded. There are 2 students, R and P. These are their names because R is rich and P is poor. And why do I call R rich? Because R wants to go to college, and R will be willing to attend college if she's funded or not. She prefers to be funded, but she's also willing to go if she's not funded. By contrast, P, the poor student, will only go to college if he's funded, and otherwise he prefers the outside option, which in this case is being unmatched, but in other cases could be a different university. Now, the final component is what do colleges want? And in this case, the rich student is a better student. She has better grades, and so the college prefers the rich to the poor. What would happen if we run deferred acceptance in this market? Well, both students will request a scholarship. The college will face the menu of both students with a scholarship. It only has one scholarship to give. So it will choose its best outcome, which is the rich student with the scholarship. The poor student will go to his second choice, but that's the outside option, and that's where the algorithm will terminate. So we'll get this matching, which is merit-based. But there's another stable matching here, another stable allocation, rather, and it's the blue one. What's going on here? The college is proposing the scholarship to the poor student and admission to the rich student, and this is the first choice of the college, and it's individually rational for both students, and so it's not blocked. Why? Nobody can convince the college to deviate. The college is getting its first choice. You'll note that first, the 2 allocations differ in cardinality, so there is no Royal Hospital theorem, and the poor student prefers the blue. The rich student prefers the red, and there is no allocation that both of them prefer. So there is no student optimal stable allocation. So what just happened? I showed you that there is enough structure in this market to run deferred acceptance and guarantee that it's stable, but the preferences are not substitutable. So all these results we know about, lattice structure, side optimality, and so on, they no longer need to hold. And I showed you that some allocations can be larger. So now we can ask ourselves, can we find the largest one? So can we do it? No, we can't. So we have a nice reduction in the paper to the stable matching problem with ties, for those who know it, which shows that approximating the largest stable allocation is impossible. This is Péter Biro, my co-author, by the way. But that doesn't mean that we can't try. So we're going to try with a heuristic. And a heuristic is called the preference flip algorithm. What does preference flip try to do? Well, we're trying to take our example, and we're trying to move from red to blue. How can we move from red to blue? Well, one thing we can do is force the rich student to say that she actually doesn't like money. So to make an obvious mistake, if you want. So what does preference flip do? It finds all the students that rank consecutively funded, unfunded, all the rich students, flips their reports to say that they actually don't like money, run deferred acceptance, check if the outcome is stable with respect to the original preferences. If it is, we stop. If it isn't, we remove one problematic person and revert his preferences back to what they were originally, and we run deferred acceptance again. So that's a polynomial algorithm. And also, it's stable because if we removed all the pairs, in the end, we're left with the empty set. We're running DA with respect to the original preferences, and we know that's stable. What is going on here? OK, so in the next part of the paper, we have a large market model in the spirit of the paper of Muhammad and Nicole. And we ask, when can we expect to have a large core, a large set of stable matchings? And can we find a different allocation with preference flip? What we show is that if students don't care about funding, let's say the scholarship is 1 cent and nobody nobody ever changes their preferences between programs because of the scholarship. There is no hope. All stable allocations have the same cardinality. If all students care a lot about funding, a lot about the terms under which they are assigned, again, you can't hope to increase the size of the allocation by meaningful quantities. But if you're in the intermediate case, where some students trade off funding and characteristic of the program very differently than others, say there are some poor students that will only go to college if they're funded, or have a lot of ranks between the funded and unfunded versions of a particular program, and other students who are not so sensitive, then there is hope, and moreover, preference flip should work. We also show that SRDA and SPDA, under any of these assumptions, will look the same. So now we take it to the data, and what we find is that preference flip increases the number of assigned students by about 2%. We have a lot of losers from the transition, but most of them stay in the same college. They just lose their funding. It's like the direct effect of what happened to the rich student in our example. By contrast, a lot of students that originally were unassigned suddenly are accepted to college. Who are these students that benefit? It's basically poor students. They come from disadvantaged backgrounds. They come from weaker localities and so on. Also, colleges in the periphery benefit a lot. So I want to make two remarks before we finish. First, preference flip is highly manipulable. I'm not trying to convince you here to implement this algorithm in any market you're involved with. It gives an obvious incentive for students to exaggerate about how much they care about funding. What I'm trying to do here is to show you that there are a lot of possibilities within the realm of stable matching, within this constraint, where you can think about ways to implement them. So maybe using AI, maybe using big data, maybe using hard information. Second, I want to say that preference flip applied local market power very narrowly using this very special case. We have algorithms that apply market power more broadly. We have algorithms that maybe because of information frictions will apply market power more narrowly, and the size of the effect will scale basically with how much market power you can apply. That's it. To conclude, I just want to say there are many other applications that involve matching with contracts. You can think about them within our framework. We wanted to stay close to the data, so we stuck with desirable things unambiguously, which is scholarships, but everything would work if you work with access to dormitories, which may or may not be desirable, and that our results say you should start maybe thinking about these classical questions that we stopped thinking about because of the small core literature. Thank you. There is a question by Bobby.
Any questions? Yes.
Victor, that was a very nice talk. One question is that, I think that in the literature, typically the thing that's done is not to adjust the preferences of the individuals, but to adjust the priorities of the schools. And this is a kind of devil's advocate argument, but in the example you gave, right, it seems if the goal is, oh, we have too many stable matchings, if you flip the priorities of the schools, right, maybe that even seems more reasonable, because I believe what it was just moving funding from one person to the other. They get the same people, the amount of money they spend is the same amount. That seems like a smaller kind of imposition on preferences in some sense, and it would seem to solve the problem, although not assigning more people because you're just killing stable matching. So I was wondering if you could talk about why you go this preference route as opposed to...
Sure. So let me repeat the question. The question was, in the literature, especially in school choice, we think about changing the priorities of schools rather than changing the preferences of students. So the answer is, we actually have in the appendix an algorithm that's what I said, applies more broadly market power, where we change the preferences of colleges. So what we do there is the college identifies students who are rich, and it just says, I have a preference list for funded seats and for unfunded seats, and I am erasing the name of rich students from the funded eligibility. And that actually gets us to increase the number of students by more. So this is definitely a direction that you could take.
Right. Any other question? Yes.
What if the funding is provided at the university level and not at the program level, and you can allocate funding in different programs?
So the question is, what would happen if the constraint on funding was at the university level rather than on the college level? This is something we don't have in the paper, but in principle, the more complex the college preferences are, the more units I can coordinate between. So what did we benefit from here is that we have two colleges, basically, two copies of the same college, that the demand for them is correlated, so a lot of people want both, and the college can apply market power. So if you think, which is true in the data, that people from a particular city may be interested in multiple programs in that city, we are allowing the college even more room to play with more students, applying more market power. So I would say probably we'll get much, much larger freedom.
Right. Yes, Nicole?
Is there a bound you can put on how large the market can grow?
I think double.
Huh?
I think double than deferred acceptance.
All right. Let's thank the speaker again.
Thanks.